There we go. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to just bless our work today. Help us to accomplish much, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So yeah, we defined the Frechet derivative last time. And it was what? Basically, you have the differential at the point of a function. It's a mapping from the vector space V to the vector space W, linear, such that what? The the limit as h goes to 0 of the difference, the change in the function, which would be f of p plus h minus f of p, is well approximated by the differential dpf of h. Now I used an L last time for that, and I do for problems sometimes, right? But we got to divide by the norm of h, right? That equals to 0. So, so we worked out an example. And of course there's a lot of questions that are begged here, right? Like, why is this the definition of derivative? How does this like tie into the, definition of derivative in calculus 1, for example? Is a pretty, pretty natural question to ask. Like, what does this have to do with derivative in calculus 1? Well, if we specialize, we can look at that as our first example. It's a natural question to ask. Like, well, how does calculus 1 appear in this story? So if we have f as just a mapping from like the domain of f, which is a subset of the reals, to the reals, right? And dpf exists, right? Then that would mean that the limit as h goes to 0, well, actually, let me take a different approach here altogether. Yeah, fine, I will behave. Okay, so we have then, what? Well, you're dead. I gotta remember to pick that up when we leave. Yeah, well, it's a linear transformation from R to R in this context. So we have f of p plus h minus f of p, and then, like you just said, since it's a linear transformation on one dimension, we can just write this as like m times h, right? So minus mh divided by, well, this becomes the absolute value of h, right? Which of course we can, we can put these up here as well if we want, but I guess I don't need to. My point is then that this implies that the limit as h goes to 0 of f of p plus h minus f of p rather, divided by the length of h, right, is equal to the limit as h goes to 0 of, mh, absolute value of h, mh over h, absolute value of h. Now, here I got to be careful because that's actually not true. See, because the limit of absolute value of h over h, the double-sided limit, it does not exist because it's 1 from one side, it's minus 1 from the other, right? But I can fix that by just going to like left-right limits right? It is true that the left and right limits separately exist, right? And this is equal to, in fact, m times the limit as h goes to 0 from the left or the right of h over absolute value of h, which I believe is, when you're going from the right, it's a +1. When you're going from the left, it's a -1. So actually, I can write plus or minus m. But then, of course, if you look at this, you have the absolute value of h is equal to plus or minus h, and the same with the plus minus is appropriately attaching. So if you look at this, you've got the left limit of that quotient, right? So, I mean, put this all together, you've got the limit as h goes to 0 from the right of f of p plus h minus f of p over h is equal to m. And you've got the limit as h goes to 0 from the left of f of p plus h minus f of p over minus h is equal to minus m. So if we put these together, right, then we have the double-sided limit of the regular difference quotient exists, and it's equal to m. And so, therefore, if the function is Frechet differentiable, it is differentiable. And not just that, it's differentiable, and if we look at the differential of p of f and feed it the number 1, well, that's equal to f prime of p, which we're calling m, right? And so, like, generically speaking, dpf of h in our current context is equal to f prime of p times h, where that's the ordinary garden variety difference quotient defined derivative in calculus 1. And these steps are reversible. You can reverse this argument. I think I have a slightly more careful version in the notes, but that's essentially it. Okay. And the same calculation works for the complex derivative. If you define your complex derivative by the difference quotient, once more, you can write the formula for the Frechet derivative in terms of the complex derivative times the complex number h. But there, that's a complex product. It's, of course, as we've talked about in complex analysis, there's more to that. This is just a plain old real product. So it's, like you said, 1-by-1 matrix. Okay, so then that's that. Let's move on. Let's see here. Example, can I erase? Yeah. Okay, cool. So, there's maybe there's a kind of theorem of Carr-Theodori we could state here as well. Maybe. I haven't tried to do this before, but I have a suspicion, which is that theorem well, let me be a little bit less adventurous here. Theorem, if f differentiable at p, then f of p plus h is equal to f of p plus the differential acting on h plus eta of h, where the limit as h goes to 0 of something is equal to 0. So let's just, we can kind of discover the rest of this theorem here, right? So I would say this is like the Carr-Theodori idea, but it's not quite the same in the sense that in Carr-Theodori, I assumed that I can like write phi of, I guess the analog here would be as if I could, the analog of Carr-Theodori here, I guess, would be if I could replace this with like phi of, phi of h, or phi of, I guess phi of h times, my current notation makes it difficult. Carr-Theodori, I would think of something like this, f of x is equal to f of x naught plus phi of x times x minus x naught. But you see, if we were going to go down that path, then these are vectors, right? So that would mean that the Carr-Theodori function would need to be like a, I just don't know. I haven't thought about this much. It's a. So I'm gonna content myself with this kind of related but slightly different Carr-Theodori-like criteria. So, look, if you solve my defining equation for eta, what you have then is that, well, if you look at it, we have f of p plus h minus f of p minus dpf of h, all divided by norm h, right, is equal to eta of h over norm h by construction here, if we have that equation. And so by assumption differentiability, we have that quotient does what? It goes to 0. So that's probably the condition we want on 8. I mean, if we write this here, then it's true by the calculation below, right?
Is that eta term like an error?
Like an error term, right? That's like the term that we saw go to 0 in our AHA calculation. Remember, like you were like, why isn't the h squared in there? Well, that h squared was the eta. I hope I'm not changing. I forget if I have this notation in these notes. I should really watch some of my videos from a few years ago and remind myself what my, notation was. Anyway, let's go on here. So, oops, come on. All right, so fine, right? Of course, and the limit as h goes to 0 of eta of h is what, equal to what? See, if we multiply this by norm h, you see that see, if I multiply this by norm h, right, I get this. I just get that, right?
It should also be minus.
Right, because this goes to 0, and this goes to well, that goes to 0. So excuse me. So it must be the eta of h goes to 0. Yeah. But anyway, the point of, well, the larger point here is for something to be a legit error term, it is not sufficient for it to just go to 0. This is a stronger condition, right? In fact, I think if this is equal to 0, it's like a fundamental like problem you could prove. If this goes to 0, it forces eta to be 0, because otherwise you'd have a limit which blows up. Okay, so great. So once you have this, theorem, if f is differentiable at P, then F continuous, that becomes really easy to prove. How do you prove that? Well, you basically just look at the sort of, we're basically calculating the limit. We'll find it convenient to calculate the limit as h goes to 0 of f of p plus h. That's, if we can show that's equal to f of p, that suffices to prove continuity, right? But what are we looking at? Well, we're looking at the limit as h goes to 0 of what? Well, f of p plus dpf of h plus eta of h. And this reminds me I need to prove something. We'll prove it in just a minute here, but this is a linear transformation. And we can prove that a linear transformation is continuous at 0, and its value is 0. So this goes to 0 by a lemma I haven't proved yet. This goes to 0 by the theorem I have on the board, and you got f of p. Thus, Frechet differentiable implies continuous. Make sense? All right, so let's prove continuity. So theorem, if we have T, a linear transformation from V to W, you know, then T is everywhere continuous. Now, I am assuming that our context is what it has been, namely that V and W are finite dimensional normed linear spaces. All right? So let's look at it, right? So I'm going to kind of construct the proof a little bit backwards by looking at what we need and then reasoning how we can do it. So essentially what we're looking for is that the norm, we would like the norm of t of x minus t of x naught, right? We would like that to be less than epsilon, given that the norm of x minus x naught is less than delta, right? If we can do that, that would prove continuity at x naught, right? That would prove the limit as x goes to x naught of t of x is t of x naught. So, all right, so here's the thing, is that we can express t of x as equal to the sum over I equals 1 to n, and the sum of j equals 1 to m of a ij x sub I w sub j. I may not have my indices quite right there. I think let me just make my indices what they're supposed to be. That's aji in our notation before, I believe. And like, of course, here A is the matrix of T with respect to our basis beta gamma, where I'm using, you know, beta to be V1 Vn, and I'm still using gamma to be W1 Wm. So I'm still in that notation scheme we've been in. All right. So the point is, we have this formula for a linear transformation, right? And so what that means then is we can calculate the norm of t of x minus t of x naught, right? But that is the norm of t of x minus x naught by linearity of t, right? Which means we can use my formula and write, well, that's really, and let's square this thing. That's really the norm. This thing. I'll just do sum of I and j, appropriately, right? A ji, xi, wj, right? Okay. But because we're going to well, I mean, we can go different ways. We can assume that the basis is orthogonal. All right. With respect, like we could assume that we're working with a but I guess I don't want to do that because I don't want to assume that the norm is necessarily induced from an inner product here, because then my proof wouldn't work, for example, in the context that we're dealing with a vector space which doesn't have a, what do you even mean by orthogonal when you don't have a inner product? Okay, so let's not do that. I'll use a different approach. So I'm going to, in view of that, no need for the square. The square, see with the square there, then if it's orthogonal, I can write it as the sum of these guys squared. But I do have a triangle inequality, right? So this is really the sum over I and j of, absolute value of a, j, I, xi times the norm of wj. So if we are working with the basis where this is equal to 1, well, let's just do that for the sake of that. That's not a big imposition. We can normalize our basis. And if we didn't, we could deal with it. It would just uglify the calculation a bit more. And if we're also working with the condition that our norm has this, right? And my bad, let me put a y here. Why? Why would I do that? Well, this is fine, but I'm letting y equals to x minus x naught to save my calculation. And so this is less than or equal to, well, the sum over I and j, right, of the absolute value of aji, the norm of y. But of course we can write that that's equal to, because well, we can pull this out, It's a constant with respect to the sum. And of course, this right here, whatever it is just some big number. We can call that m. For a given linear transformation, that number exists, and so this is less than or equal to m times the norm of x minus x naught. So we simply choose delta equal to, epsilon over m. Right? And if we do that, then given the condition that x is within delta equals epsilon over m so defined units of x naught, then that implies that the t of x minus t of x naught is less than epsilon for arbitrary epsilon. Assuming, of course, we're working with a normalized basis, which isn't too big of an imposition. If you weren't working with a normalized basis, you could define like the maximum of the norms of all the elements of the basis and build that into your estimate. So yay, if t is continuous everywhere. Now, of course, you could also prove this by just proving it at like 0 and then using like a shifting argument. I think you could do that. But I think it's more fun to just prove it. All right, great. So now, for the rest of this course, we have proved that linear transformation. Uh-oh. Is there a course in here now?
Oh, I think we have at 10:30 for
10:30, okay.
But you're good, Helen.
Okay. 10:30? I'll get out of here by 10:30 then.
Okay.
Yeah, thanks.
I appreciate it.
Rats. What time is it?
10:20.
Oh, son of a gun. All right, well, we've proved it's continuous. I guess we'll pick up again here in another room eventually.